All right, so for the halogenation mechanism, step one is initiation. We must produce free radicals. And that is the purpose of the ultraviolet, production of free radicals. And then we propagate the reaction, and then finally it terminates. So step one, initiation. Ultraviolet splits chlorine into two free radicals. And then propagation. A free radical comes into a compound and removes a hydrogen radical, leaving a methyl free radical, which will then bump into another chlorine, producing chloromethane and another chlorine radical. And and this happens over and over and over and over and over and over again, because you start with a chlorine radical and you end with a chlorine radical. And it does it over and over and over again. Which is why this was so dangerous with the ozone layer, because these molecules act as catalysts and keep propagating, and the reaction keeps going. In a termination reaction, two free radicals accidentally bump into each other, quenching the reaction and removing the free radical which was propagating the reaction. Free radical stability. Tertiary free radicals are the most stable. So this is the most stable free radical. Secondary is the second, and primary is the least stable of these three. Halogenation. Your major product is typically from the most stable free radical, and the minor product is from the less stable free radical. So in this case, our major product is going to be 2-chloropropane, because that's a more stable free radical. The minor product is 1-chloropropane, because that's a less stable free radical. All right, so write an equation for each step in the free radical mechanism, forming 2-chlorobutane from butane and chlorine in the presence of light. Step 1, initiation. Ultraviolet light rips apart chlorine into two free radicals. The free radicals then bump into butane, and they take off a hydrogen radical, leaving a butyl radical, which then bumps into chlorine, removing a chloro radical and removing a chlorine and leaving a chloro radical. And then this can happen over and 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 over again, until you finally get a termination reaction, in which two free radicals accidentally bump into each other, quenching the reaction. Sources of alkanes. Alkanes are produced from natural gas and petroleum. So alkanes all come from fossil fuels that are in the ground, and geologists learn how to find them. Gasoline is a mixture of hydrocarbons, and the knocking of gasoline is the detonation of the air-fuel mixture in an engine. And so the octane rating is compared to a hypothetical performance mixture of isooctane and heptane. And so you don't actually just have isooctane and heptane in the gas, but the detonation and the performance of the gasoline is compared to specific isooctane-heptane mixtures for calibration. So over here we see all kinds of hydrocarbons that we find in gasoline. Gasoline additives boost octane ratings. We used to use tetraethyl lead, but we can't use it anymore because lead is absolutely terrible for the environment and is toxic to people. So lead was discontinued, and so all fuel today is unleaded fuel. You can still get leaded fuel for race cars, but it's not allowed on the streets, so it's not street legal. And then methyl tert-butyl ether was used, and this is methyl tert-butyl ether, and it was a great product. The problem with it is that it's water soluble, and a lot of gas stations are leaking. You don't notice it, but below a gas station are gigantic tanks which hold all the gas at the gas station, and a lot of those are really old and leak slightly. And so this could get into the groundwater. And this was water soluble, and so it was infiltrating groundwater, and so it was discontinued. And so these days we use ethanol, because ethanol does a great job boosting octane ratings, and it's not toxic for people. So even if there was a slight leak, the amount of ethanol that gets into groundwater is nowhere near what you'd be exposed to just by putting mouthwash in your mouth. And so it got rid of the safety hazard, and that's why we all switched to ethanol, because it does a great job and is extremely environmentally friendly, and in micro amounts does not hurt people whatsoever. Cycloalkanes. Here we have cyclic alkanes with the formula CnH2n. And here we have cyclopropane, cyclobutane, cyclopentane, cyclohexane. They're similar to alkanes, but cyclopropane and cyclobutane are more reactive because the bonds are so constricted. These bonds want to be 109.5 degrees away from each other, but they're actually 60 degrees away from each other. These are 90 degrees away from each other. So these two chemicals, because their bonds have been scrunched into a much tighter conformation than they like, are extra reactive. So again, cyclopropane and cyclobutane have higher reactivity because of strained bonds. So they react really easily. And so here it reacts with bromine very quickly. Cyclohexane. We have two conformations. We call them chair and boat, because this kind of looks like a lawn chair, and this one kind of looks like a boat. And it flips back and forth between these conformations. So draw the structure for two cycloalkanes that have the molecular formula C4H8. Well, it can be cyclobutane, C4H8, or methylcyclopropane, also 1, 2, 3, 4, 5, 6, 7, 8 carbon or hydrogens. So both of those would be cycloalkanes, because one has a cyclobutane group, one has a cyclopropane group, and they're both C4H8. Monosubstituted cycloalkanes. We name the substituent and then we name the cycloalkane. So methyl cyclohexane. If there's more than one thing coming off of the cyclohexane, we name the ring to give the numbers, to give the groups the lowest possible number. So this is 1,1 dimethylcyclohexane, 1,2, 1,3, 1,4. This is back to 1,3 because we can count the other way. You wouldn't say 1,5 because 1,3 are lower numbers. This is back to 1,2. So you always give the numbers to give them the lowest possible numbers. So write structural formulas for 1-bromo, 2-methylcyclopentane, and 1,1-dichloro, 3-ethylcyclohexane. Well, 1-bromo, 2-methyl. 1, 2. And 1,1-dichloro, 3-ethylcyclohexane. We have chlorine both at the 1 position, and then at the 3 position, you have an ethyl group. 1,1-dichloro, 3-ethylcyclohexane. And that is the end of this chapter.